Today we're going to move into the world of second-order differential equations. And I want to motivate those second-order differential equations with an example from physics. So I'm going to consider a mass attached to a spring with a spring constant, K. So I'm going to attach a mass on a spring to some sort of wall. I'm going to let it sit at rest. So I'm going to let that position of rest be 0, and then I'm going to let it move along the x-axis. I'm going to assume for the moment that there's no friction on the surface on which that mass moves. And essentially, I'm going to displace that spring. I might stretch the spring, or I might compress the spring, and then I want to describe the behavior of the mass on the spring. A key fact that describes the movement of the mass on a spring is Hooke's law. The restoring force of a spring is proportional to its displacement. So in other words, the force on the spring, or the force exerted by the spring, is proportional to the displacement from its natural resting point, which is x. So it's a constant times x. But it's a restoring force, and that force is actually going to be negative. That constant is going to be negative. And that is because if you imagine, if you have a mass on a spring and you were to compress the mass, so move it in the negative direction, then the spring would exert a force back on the mass in the positive direction. But if you were to stretch the spring, to move it in this direction, then you expect the spring to exert a force that pulls it back towards the wall because it wants to be in its natural resting spot. Okay, and so it's always going to be exerting a force that restores the mass on a spring back to its resting position, and that's going to be the opposite direction that we displace the mass. Okay, if we apply Newton's second law, that says that mass times acceleration is equal to the sum of the forces, and the only force that's being exerted on the mass is the restoring force of the spring, which is minus k times x. So we can actually rewrite this if we divide by m as x double prime plus k over m times x is equal to 0. So this gives us a second order differential equation that we want to investigate because there's a second derivative on our function x. So we're going to try to solve equations of the form x double prime plus or minus omega squared x equals 0. So in our previous example, we actually would be letting omega squared equal k over m. And it'll be clear in a moment why we decided to replace k over m with omega squared as we solve this equation. So what I want to note from this equation is that the second derivative here is equal to a multiple of itself. Okay, so we have that the second derivative is a multiple of itself. So what we're going to try to do is we're going to try to guess the solution like we did with our first order differential equations. Okay, because we know something about the form of the derivative. It's a multiple of itself. So what I would like is some sort of starting point, some sort of key approach. In German, that's called an Ansatz. And that is, what function has a second derivative that is a multiple of itself? Well, before we saw that when the first derivative was a multiple of itself, we used an exponential. And if that's true for the first derivative, it's also true for the second derivative. So the best guess here is that x of t is e to the lambda t, where lambda is some constant. So in order to show that that is indeed a solution, I'm going to want to substitute that into the differential equation. So I'm going to take the derivative of x, which is lambda e to the lambda t, and I'm going to take the second derivative of x, which is lambda squared e to the lambda t. And I'm going to substitute that into the differential equation. So I have x double prime plus or minus omega squared times x is equal to 0. So that tells me that lambda squared e to the lambda times t, it's substituting for the second derivative, plus or minus omega squared e to the lambda t, substituting for x, is equal to 0. Another way to write that is that lambda squared plus or minus omega squared times e to the lambda t is equal to 0. Now that's only going to equal 0 all the time if lambda squared plus or minus omega squared is equal to 0. We could say that lambda squared is equal to negative omega squared, or that lambda is equal to plus or minus the square root of negative or positive omega squared, if we like. So we have figured out what the constant lambda should be. Okay, it should be plus or minus the square root of a negative or positive omega squared. So that really gives us two cases. One where that square root is going to be a real number, and one where it's going to be an imaginary number. So let's move into that first case where we're going to get a real number. So if we look at the equation x double prime minus omega squared x equal to 0, in that instance, we have that lambda squared minus omega squared is equal to 0. That tells us that lambda squared equals omega squared. So lambda must be plus or minus omega squared. Okay, so in fact, lambda equals plus or minus omega. So in fact, that actually gives us two solutions. I'll call one of them x plus, which is going to be e to the omega times t. And the other one I'm going to call x minus, which is going to be e to the minus omega times t. And both of them are solutions to this differential equation. So the question is, which one should we choose? And the answer is, to come up with a general solution, we should actually take a linear combination of both. X of t should be a constant multiple of e to the omega t plus another constant multiple of e to the minus omega t. Now, the reason why we want to take a linear combination of these two solutions will become more clear when we look at it in the next video. But for now, take it on faith that that is the general solution. In fact, you can substitute that general solution back into the differential equation, and you will see that it is indeed a solution. Now, that's one way to write the solution, okay? But we could write it a different way as well. We could, in fact, think about C1. If C1 was a half and C2 was a half, then we could create a solution x1, for example, which would have been e to the omega t plus e to the minus omega t over 2. And we've seen previously that's actually the hyperbolic cosine function, or cosh of omega t. Or we could have done C1 equals C2 equals negative 1/2. And that would give us a different solution, x2 of t, which was, excuse me, that's not quite right. We could have done c1 equals a half, c2 equals negative a half, and then x2 of t would be e to the omega t plus e to the minus omega t, all we want to do e to the omega t minus e to the minus omega t over 2. And that would be the hyperbolic sine function of omega t. So you can actually show by taking two derivatives that both the hyperbolic cosine function and the hyperbolic sine function are solutions to this equation. And so that the general solution could be written as x of t equals c1 cos of omega t plus c2 sinh of omega t. So there are kind of two ways that we could write this solution. One is in terms of exponentials. The other is in terms of hyperbolic cosines and sines. Okay, that's case one. Let's look at case two. That's where x double prime plus omega squared x is equal to 0. So here we have that lambda squared plus omega squared is equal to 0. That's saying that lambda squared is equal to minus omega squared. And then if we take square roots, we're going to need imaginary numbers. In this case, lambda would have to then be plus or minus I times omega. And so that gives me two solutions. Those two solutions are going to be x plus, which is e to the I omega t, and x minus, which is e to the minus I omega t. But both of those solutions involve complex numbers. And so how can a problem that has a real application, okay, this is the problem that we had before from the mass spring system, where we're going to have a spring that's oscillating. How can that problem, okay, where we've let k over m be omega squared, how can that problem that describes a real physical phenomena have a solution that involves imaginary numbers? That just doesn't quite make sense. Well, why don't we do the same thing that we did before? Why don't we take linear combinations of the solutions and see if we can get something that's real? So I'm going to let x1 be x plus x minus over 2. Okay, so think about that. That's e to the I omega t plus e to the minus I omega t over 2. Well, we saw that that's actually the definition of cosine of omega t. And then x2, we could let be x plus minus x minus over 2i. So I'm going to take a linear combination of x plus and x minus. Notice that I'm going to allow for an imaginary number in that linear combination. That would be e to the I omega t minus e to the minus I omega t over 2i. So that would give me the sine of omega t. So I actually have two solutions, cosine and sine. And you can plug those back into the differential equation, noting that the second derivative of cosine is minus omega squared times cosine, and the second derivative of sine is minus omega squared times sine. So they are solutions. So our general solution to this problem is going to be x of t equals c1 cosine of omega t plus c2 sine of omega t. Okay, now that we've solved these second order differential equations, in the case that we have a minus omega squared and a positive omega squared, let's go back to that mass spring problem idea. Okay. Here, a 5 kilogram mass is attached to a spring hanging from the ceiling. Suppose that the gravity naturally stretches the spring by 0.2 meters. Okay. So what I'm going to do is I'm going to hang a spring like this and attach a mass to it. And I'm going to note that it naturally stretches the spring by 0.2 meters. So in this case, instead of x, I'm going to use y as my axis. Okay. Okay, so that's going to be y. Okay, so the mass has essentially two forces acting on it. Okay, there's a force of gravity that's acting on it, which is equal to mg, and then there's a force due to the spring that's acting on it, and that's equal to k times x. Okay, so here we're making a diagram of the forces. Okay, in the center we've got the mass. We have a force of the spring. It's essentially pulling up, and gravity is pulling down. So if the spring is not moving, okay, we have that these forces are evening each other out. They're balancing each other. So then the force of the spring has to equal the force due to gravity. In that case, we have that k times x has to equal m times g. So this gives us a way to essentially to solve for k, because k is going to equal mg over x. So this is a 5 kilogram mass. So m is 5 kilograms. Gravitational constant is 9.8 meters per second squared. And we're going to say that that would stretch it by 0.2 meters. Okay, so this gives us actually 245 kilograms per second squared. And that's actually the spring constant, K. So this description allows us to get at the spring constant, K. Now, from that, we want to come up with an initial value problem. So what is our initial value problem going to be? Well, what's our differential equation going to be? So we're going to have x double prime plus k over mx is equal to 0. So our initial value problem is actually x double prime plus 245 over 5 is 49. X is equal to 0. Now, what other conditions do we have besides the differential equation? Well, it says find an equation that describes the motion of the mass if it is stretched 0.1 meters and then released from rest. Okay, so I'm going to make sure that I understand what my axes represent. So I guess I'm going to stretch it 0.1 meters. So I'm going to let y point up here. That's going to be 0. I'm going to stretch it 0.1 meters to there. So that's going to mean that x of 0 is going to be negative 0.1 meters. And then I'm going to release it from rest. That means there's going to be no initial velocity. Okay, so that's going to be x prime of 0 is equal to 0. So here, this is releasing from rest, and then this is stretching 0.1 meters. Okay. Well, now I need to solve the differential equation, and the general solution we saw was going to be C1 cosine of omega t. Omega squared is 49, so omega is 7t, plus C2 sine of 7t. And then you ask yourself, what are C1 and C2? Well, we can use the initial conditions. X of 0 is C1 times the cosine of 0, which is 1, plus C2 times 0, and that's supposed to be negative 0.1. So C1 is just negative 0.1. And then we have that x prime of 0 is the other thing that we need to pop in. So x prime of 0 is going to be negative 7c1 sine of 0 plus 7c2 cosine of 0. So that's actually going to be 7c2, and that's going to equal 0. So that tells me that c2 is 0. So my general solution is going to be that x of t is going to be negative 0.1 times the cosine of 7t. So what that tells us is that our spring starts at negative 0.1 and has a negative cosine curve to it. So it just oscillates forever. And that's because there's no friction. So it's just going to keep oscillating forever. That gives us an idea of what the mass on a spring will do. You expect that if you stretch it, that it'll essentially oscillate with a periodic motion forever if there's no sort of friction or air resistance. Let's see what that looks like, say, in slopes. Okay, so I need to set the initial condition. So I set, this is a y double prime, a is 1, and then b is 0 because there's no y prime in our equation. C is 49 because that came from our equation. Okay, and then our initial condition is actually a negative 0.1. Okay, and so what we're going to do is we're going to stretch the spring and then we're going to release it. So we can actually play a simulation using the play button. It's going to stretch the spring down, and then we're going to watch the spring oscillate according to that cosine curve.